Greetings. Welcome, everybody. We are going to have Dr. Dagtus pick up where he left off on Tuesday. So we will just start off with these slides. And I was going to say, very good. We'll just, excellent. Oh, I wonder if they have a way that we can go. Oh, we can't.
Fast forward, yeah.
Yay. So, yeah.
Okay, I can go back a little bit and just adjust that.
Yeah, adjust as needed. Okay, fantastic. All right. Very good. Excellent.
Okay, guys, we turned the camera off so you have more bandwidth for the audio and the presentation here. But let us know if you have any questions or if you would like to add anything at any point. I believe you should be able to see the screen. So just a quick refresher. We started out with the very basic representation of images in the digital space. And we talked about, the three main components of that: sampling, coding, etc. Color representations, what they represent, alternative color models. So this color cube, you may find this also interesting. The RGB space can be represented by a color cube, and most of the colors that we can see and perceive are represented by a dot within this three-dimensional color cube, basically. And this diagonal axis here represents the gray color, from going from pure black to pure white and all the shades of the gray in between. So you sometimes see illustration of the color models, color space, three-dimensional models like this. And I did show you from this PowerPoint tool also a somewhat three-dimensional representation of RGB, HSL, YUV color models, and how you can convert one color to another. And in the HLS space, there is a hexagon model that's sometimes used to visually represent different colors at different corners of this three-dimensional space. So this is just an alternative way. So the different color models capture different aspects, physical aspects of the color spectrum in different ways. So one may be more convenient than other, depending on what you're trying to do and how you want to represent the color. But it comes down to a three-dimensional representation of the color values at every pixel, no matter which color model you use. So these are some low-level descriptions, of the digital images in terms of pixels, and then each pixel is represented by a color value. But you need to go beyond that, obviously. So to assign a meaning, or to capture a description, or to build an AI or data-centric applications, you need to go beyond what the pixels, zeros and ones, etc. So we'll take a quick look at some of these representation and description models on which you can possibly build some kind of a smart application, smart purpose, or AI application, or databases, etc. One of those higher level, and you can go in the hierarchy from very low level, pixel level representation to very high level of knowledge and wisdom and all that. But in between, you have some intermediate steps. So those descriptors will help you define and build some of these AI and learning models. Defining regions or shapes are one of those key intermediate representations or descriptions that you can build. So you can basically grow, for example, just combine different pixels and develop regions and represent region-based representations, shapes, edges sometimes. So you can, for example, come up with simple answers to some simple questions like how do you differentiate between an orange and red apple, whether an object represented actually an apple and banana. So if you ask these questions to yourselves, you typically go with either the dominant color or the general shape. If something is a round shape, you hardly would call it a banana, even if you can barely see it, right? So you have some model representations in your mind, and then of course you try to fit what you see or perceive to those. Similarly, some of these boundary region-based representations, which are not only more space and data efficient, but also more towards defining the objects, etc. So boundaries can be represented in different ways, like chain code representation, etc. A region is typically a collection of pixels, basically connected components. So there are different techniques to represent boundaries. Some of these are captured in the sample projects that you can take a look when you, for example, apply certain filters for edge detection. Those filters can be Fourier-based filters or similar filters that best captures the edges and allows you to detect boundaries and represent them also. The regions also likewise can be represented by in different ways using topological descriptors, defining the texture sometimes, and moments. So we won't get into the details of everything here, but the representation schemes like chain code representation, so stepwise the descriptions of the boundaries or edges, in other words, can allow you to represent your shapes and edges in a very efficient way, and also can be independent of certain aspects like rotation or even scale, and basically representation of larger or smaller objects in a similar way. So you can basically obtain some kind of a reliable similarity metric between a small object of the same kind and a large object. So some of these requirements or necessities can also be answered by some of these representation schemes. Fourier transform, you may be familiar with this, is one of the most popular frequency domain representations or transformations. With these Fourier coefficients, you can actually represent not only the frequency components, but also the edges and boundaries in a more efficient way. And moments are somewhat similar to that, and it can basically give you a histogram-based representation of edges. I think this much detail is enough for our purposes in this class, but let's take a look at an example of region descriptors, which may equally be interesting. So you basically define certain areas within your image in terms of which pixels are part of that. So if you're, for example, trying to detect faces from videos or images for further processing, like face recognition or for any other purpose, you would want to identify the regions that represents potential candidates, right, for the face of a person by skin color detection, and then maybe applying some further analysis and processing techniques to ensure certain parameters like compactness. So these two areas, as an example, they may have the same area, like size-wise, etc., but one is more compact, one is not. So this compactness and some other factors are taken into account in defining a region, categorizing them, and then defining some kind of similarity metric for applications like face detection, face recognition, or other object, determination of other objects, etc. So representing the objects in terms of regions rather than just pure raw pixels obviously allows some of these more advanced or more smart applications to be in place. Texture is another dimension of defining an image or qualifying the contents of an image. So sometimes, a lot of times, in fact, in real world, you have not just the uniform color regions or surfaces, but rather some kind of a texture with some repeated patterns in some cases, with different features of levels of smoothness, coarseness, etc., regularity, etc. So most of the natural imagery, in fact, have some kind of a texture description which can be identified and can be also represented by their histogram values. So I did mention this face detection as one example and interesting concept. So people are interested, of course, objects in the images and videos, and their faces are typically the most interesting part of the regions in an image that represents a person. So this face detection algorithm, as an example, starts with the skin color detection. Well, this is what most people would do, of course, taking into account all kinds of variations in defining a skin color. But just going by the color representation typically is not very efficient or enough. So you may detect a lot of areas, for example, the coat this lady is wearing may have colors very similar to the face. So you can't just rely on the color specifications, color-based detection, obviously, and representation. So you would not need to go through some kind of a segmentation or iterative algorithm or methods to filter and increase the both accuracy and, of course, the efficiency of your solution too. And typically at the last stage, you want to, once you have different segments as identified as potential skin color or face area candidates, the grouping stage can actually get you the most accurate and most reliable results. So this shows you some techniques to kind of choose within the three-dimensional color space the potential areas or regions of color values that may belong to a skin color area within your images. Shows you some examples of good ones and not so successful ones just based on skin color detection. So segmentation and further processing can take this skin tone or skin color candidate segments and basically refine your results to better ones, but that may typically not be still sufficient. So grouping and making sure that you are taking into account only the most likely parts or segments of the image as a potential face area will give you finally the potentially the most accurate results. And this grouping can be done based on the distances in the color space, just like operating in the frequency domain for different purposes like filtering or coding or compression purposes. The graph representation of these color segments can actually give you a good basis for the grouping and combining the different segments. And finally, leaving some of the details out, you may actually come up with the most accurate region for what may constitute a human's face after all this processing. And then you can move on to the next phase of trying to identify this person, recognizing who they are, maybe getting into the areas like trying to capture their gestures and maybe even speech recognition from their lip movements and things like that. So this processing can, of course, go further to higher levels of understanding the image content, or in fact, if these are video recordings, of course, the video content also. So you see some examples on how this application or this idea can work best. So we went through some example areas, starting with the very basic the definition and description of image videos, to some further processing ideas on how you can utilize these. And the area is, of course, large. We just touched on some examples, and I'd like to continue that with other components of multimedia data, basically audio and video. So this is a different set of slides now we are viewing. But if there are any questions or comments from what we have seen so far, let us know. So we're going to look at some audio and video specific aspects, and in continuation of what we have discussed on Tuesday and also today, we saw some of these slides. So this signal from analog signal to digital representation, same ideas apply to audio signal as well. Obviously, this is a one-dimensional signal rather than the two-dimensional XY coordinates that you see. But the digital representation of audio can also lead to many applications, like speech, encoding of speech, obviously, for storage purposes, and also recognizing the text as well as the identity of the people, or perhaps the context from speech or audio signals. And of course, the inverse of some of these techniques can also allow you to text-to-speech, build text-to-speech application for the synthesis of speech. So digital representation of audio, following the same three basic steps of sampling, quantization, and coding, can allow you to build some of these higher level applications using audio as another dimension in multimedia systems. So music, of course, is a special form of audio. So when you record music from just real-world audio tracks, you can represent that with the audio encoding mechanisms. But you may also have, just like the vector graphics for visual data, music in the form of similar standards can also be represented with objects rather than actual audio recordings. So this can obviously give you a more efficient storage, ways to edit, since you have basically objects, different instruments, timed in different ways. But other than standards, object-based standards like MIDI or similar music-based standards, most of the audio signals will be sampled, quantized, and encoded into digital streams, as we know. And if you have stereo left and right channels, this will basically give you two channels or two streams to digitize, or if you have multiple channels, the same thing. But audio essentially is a one-dimensional signal. The way we hear data, audio, the way we perceive it, of course, is in the form of vibrations, movements. So these vibrations or amplitude levels can be sampled at certain intervals and turned into a stream. One trick with this sampling, whether it's for audio or image purposes, is that you have to be fast enough, right? In other words, your sampling frequency or the intervals should be sufficiently high or the intervals sufficiently low, so you capture your data, and when you recover it, the way you recover or reproduce should be a correct one. If you're below that critical frequency, you run into what is called an aliasing concept. For audio signals, that can of course distort the signal. What you hear back after sampling, it will not be the same or nearly the same as the original one. So you can basically see the effect of aliasing or undersampling in this representation. The continuous signal here is the original signal. If your sampling is not fast enough, in other words, if you're not getting enough samples per cycle, then when you connect the dots at a later point, the signal that you're recovering, this is the dotted lines, is not same as the original, right? So the question here is, considering the continuous signal, the higher frequency signal, the original signal, how many samples would you need for each cycle of the original signal? So each cycle is, you have the positive part, negative part, you come back to zero. This is one cycle, right, between two zero crossings. So for a long time, people thought or assumed that you would actually need one sample per cycle, which is not the case. Just by looking at this, and can anybody guess how many samples would you need to collect from each cycle at least? So when you connect the dots, obviously this example shows you, hugely undersampled, right? So when you connect the dots, the signal that you recover is not nearly as good as, in fact, you're missing, in fact, a good chunk of it. By the time you complete one cycle in the reproduced signal here, you have actually gone through, what, 6, 7 cycles? So you're
almost looks like,
badly undersampling.
Yeah.
How many samples per cycle would you need not to fall into this kind of a situation? At least one, but that's still not sufficient, right? So, but it turns out, and this is called Nyquist frequency, that's the person who came up with the idea, you need to have at least 2 samples per cycle of the original. So to guarantee that you can, by connecting these dots at a later point, you actually are recovering the same signal originally. If you don't do that, you run into some problem. In videos, you may have noticed that in older Western movies, the wheels moving backwards. That's an aliasing problem, right? Because by the time the next frame is captured, the wheels actually turn more than one cycle. So the spokes are caught in their next cycle, just like this example shows. So the impression you get is as if the wheels are turning backwards rather than forwards, which in fact, in reality, they're moving forward. So those older movies were, of course, captured at lower frame rates, 30 frames per second, etc. So fast-moving objects like those, the carriages and their wheels would actually reveal this issue. If you're watching basketball, sometimes their referees wearing stripes. If they turn around too quickly, for even in higher frame rate videos today, their shirts will have some distorted image. Right? So that's also another example for aliasing, undersampling in the time domain. So your sampling needs to be at a certain frequency. This is called Nyquist, at least half of the frequency, or at least 2 samples per cycle, not to fall into the undersampling problem. So if you're within that range, you wouldn't have any problems. If not, you have what's called an aliasing, which will distort the signal. So once you have enough samples, whether it's an audio signal or image, then you would need to quantize all the sampled values would have to be represented in digital format. We know this is done with RGB values for color images. For audio, similarly, you spend a number of bits or bytes for each sample point. So the question here is, what is the Nyquist rate, do you think, for the audio signal? So in order to recover an audio recording. So digital audio first became popular with the CD recording, CD standards, when the CDs came out in the 80s, early 80s, I guess. So there had to be some standard, right, for sampling and digitization of the earlier analog recordings. So, and there was this concept of CD quality audio, which called for a certain sampling frequency and representations. So it was 16 bits per sample, and the frequency or sampling frequency was at 44.1 kilohertz. Does anybody know why? You're looking it up.
Yeah.
So 44.1 kilohertz. Where does that number come from? Any ideas? And it has to do with this aliasing issue concept. Why is CD quality audio or CD audio standard called for 44.1 kilohertz? It's an odd number at the round figure, but with just keeping this Nyquist frequency in mind, where do you think that 44.1 kilohertz? Kilohertz means 1,000 hertz, right? So you can imagine this 44,000 hertz. And 1 hertz means 1 cycle per second. So that simply means you obtain 44,000 some change samples per second when you go from all real-time analog audio to digitized representation. So, and imagine this: the sampling rate, the frequency needs to be at least twice the highest frequency that you want to sample, so you don't lose any data, right? So what's the deal with 44.1 kilohertz? Does anybody know? Or anybody would like to take a guess? It should be at least twice as something, right? What is that something? The audio signal has many frequency components, low end, medium, etc. So when you use an equalizer, you suppress and amplify some frequencies, so you get a better mix of different frequencies, so the quality of the audio will be different. But there is a highest frequency that we can hear as humans.
Oh, okay.
And that highest frequency for most people is around 20 kilohertz.
Oh, okay.
And dogs, as you know, can hear actually higher frequencies. So they have these dog whistles. Has anybody tried one of these? When you blow into those, some people hear more or less, but you can hear a very faint, high-pitched sound.
Yeah.
But most of the frequencies we cannot hear, but the dogs can, so you can use them, to call dog. So the highest frequencies for most people fall in the range of 20 kilohertz, plus minus maybe a couple. So 44 kilohertz, in that sense, guarantees that you can recover all the frequency components up to 22 kilohertz. Anything above that would be distorted because of aliasing, but we don't care because we don't hear them anyway, right? So 44 kilohertz in that sense is generally enough to digitize audio for at least for humans. But if you were recording a CD for your dog, you better sample them at a higher frequency. But for humans, 44.1 kilohertz was good enough. So you go from that sampling to quantization. You have this representation of your image or audio, etc. And then we saw that for images, you can capture more higher level features like regions, etc. And then you can go to object recognition and so forth. But what can you do, or what do we need to do differently for audio or video streams? Obviously, with videos will. Okay, there's a comment about audio recordings, especially for dogs. Keeping the signal processing concepts in mind. So video, of course, can contain a lot richer information, right? So you have not only just image representation, but also the changing dynamics and the visual components, as well as, of course, the addition of the audio and all kinds of semantics and information that can be added. So we are going to look at some of those video specific aspects that are not necessarily the case for still images in this part. And obviously there's no need to, I guess, stress this, but videos on many social media platforms and through other means, digital videos, are becoming just as important and relevant as the other types of data. In fact, in some cases, even more so. So video will have not only just still images, but the highly correlated sequences of images along with audio track, and in many cases, even text or metadata descriptions too, represented in text. So you will need to take into account different dimensions of data representation, both the visual image representation of obviously what you can obtain from audio. Sometimes they cross-correlate them, and even text, whether it's speech-to-text transcriptions or the screen text that may actually be part of your images, or metadata descriptors, etc. So many of these dimensions, text, metadata, audio tracks, content of the images or audios itself, will need to be taken into account. And many methods are interestingly found to be able to work better when you adopt an integrated approach, taking into account multiple streams that will typically be very highly correlated. So, for example, the transcript of the audio track and the visual contents together may give you much better results. And that's true for the metadata descriptors also, that may be either manually created or in some cases automation based. So you can look at these video management or retrieval or indexing methods from different contexts. Text-based methods resemble very much what you do with the text or the traditional data science techniques, of course. In this case, your data domain is either transcripts, subtitles, screen data, or the metadata. So you can use the traditional information retrieval and representation and data science techniques here. So there are some examples here on how you can, for example, turn your news broadcast videos into text databases and apply some of the text-based methods. But it becomes interesting when you not only treat them as the transcripts as a text-based database, but take into account also the audio or other tracks for maybe higher level or more ambitious goals.
Yeah.
So you can take the audio track and not just to convert that into transcripts, to turn that into a text-based database, but also capture some non-verbal aspects of the audio track. So that can add, of course, a whole new dimension, new component, and you can also add on top of that as another track, which is even richer in its semantics, the video or visual track, which can either be treated as a collection of images. You can at least do that. So take sample images, and the image content can give you some representation of what is contained in that image. And of course, even further, you can look at the entire sequence as a whole, with the correlations involved, and look at motions, etc. So look at the video specific aspects of that semantics involved. So many multimedia-based systems will actually combine, even within the video data itself, which in itself, multimedia, context, many applications, AI or data science applications, will typically combine or integrate multiple streams or multiple tracks.
And I'll just pause. That whole sound analysis is really interesting. I mean, I've seen apps that have tried to identify birds based on listening to their chirping and then identifying the bird. You think about these applications that are trying to distinguish between, is it a gunshot or is it fireworks? Right. Or is it a car backfiring? Sure. And I was going to say in the biology area, they're finding that if they go even deeper, they can actually, when we hear a barking dog, it may all sound like barking dogs, but they can actually, it can be like a fingerprint if you go down deep in more detail to be able to precisely identify the sound pattern.
And you can try to solve that problem by relying on the audio track alone.
Yeah.
That would be one way. But if it's a video recording, obviously the visual data combined with the audio track can, in many cases, give you the most accurate. So what you're seeing is a fireworks. The sound that may sound like gunshot will actually be interpreted more correctly as fireworks, just taking the visual track
Yeah.
into account, or dog barking, etc. So there are some simple cases where we're using multiple sources, multiple tracks, or into account, resulting in higher accuracy or precision. And in many cases, like person identification, this can actually be even more relevant. For example, gait analysis, identifying a person from their movements or walking can be more, precise.
Yeah, supposedly that's very unique. Yeah.
Just voice-based identification and things like that. So just like the images are represented by regions, etc., the video data management systems will also treat video in terms of different segments that will involve parsing using different techniques. You can just use, basic image features for that, maybe camera shots, etc., equal intervals, or you can do these parsing or segmentation techniques based on higher level features like identification of persons, so the segments of video where a specific person is present, for example. So different features, low, medium, or high level features can be used to index video segments, just like data indexing is used in traditional databases. The visual or other aspects of video data can be incorporated into indexing mechanisms and techniques, especially from the user's perspective. Retrieval and browsing techniques have been developed. So just like the SQL language for alphanumeric data, how do you represent what you're looking for in a video database management system? And how do you allow users to basically go through the results, maybe refine, provide some feedback? So many data management tools actually address some of these fundamental concepts in terms of processing and incorporating video data into a data-centric application. So scenes, shots, and frames can be the units depending on the granularity and the purpose in video parsing. So maybe consist of, just like individual pixels, you start with pixels and then you generate regions and then both objects and still images. Likewise, in the temporal dimension, you can start with individual frames, combine them into related shots, and then shots together may possibly define. So you can define a hierarchical representation of the collection of frames that will eventually make up the entire video stream or collection. And these can be at different levels of granularity, the units of your data management system. And usually when you're identifying frames, this concept is also used in video compression techniques to identify certain frames as so-called keyframes. When you're fast forwarding or rewinding your digital stream, sometimes as you do that, the DVD players or the DVD or digital video playback applications will also do this. They allow you to basically see certain frames every second, every 2 seconds, etc. Similar to that, but keyframes can be selected at fixed intervals, or you can be a bit smarter and choose a representative frame for each shot or segment. And there are many techniques around this too. So for keyframe extraction, so each frame basically is the idea is to pick up a frame that is best representative of that shot. So you can have just a single image representation, and this will allow users to quickly browse through and maybe zoom into what may sound more interesting. And also it may give you the boundaries for which you can use to define shots and scenes. So depending on the purpose and the context, keyframes are captured and extracted using different techniques. But from especially a human user's perspective, an image representation of a sequence of frames can be useful for many situations. So just a typical video data retrieval scenario can involve the test data. This is the video stream. Both your query, which may be another video shot or video clip, they can both go through the same shot boundary and feature generation mechanism, which will then generate a set of feature vectors. These numbers are just representative. So you can have some matching or distance measurement or retrieval mechanism based on those features, obviously. So you're not just matching pixels to pixels or anything like that. This would, first of all, be too time consuming, and it would probably give you very little useful information. But if you have some kind of a dimensionality reduction by capturing the most prominent, most relevant features, these could be either color histograms, color-based general descriptors, or more specific object-based descriptors, and so forth. So using some kind of a feedback mechanism, you can refine your retrieval results, or sometimes, there won't be any feedback, but using some kind of a similarity metric between the feature set that you obtain from your query and the feature set that already exists in the database, you would come up with the best set of similarity, just like basically the web searches that you do based on keywords, numbers, etc. In this case, instead of comparing words, capturing the semantics in alphanumeric data, you're trying to capture that semantics in the visual or audiovisual domain, which can be tricky. Of course, many different techniques have been used and developed, and this is an active, ongoing research area. But this would be the basic idea of matching what you're looking for to what is in your data collection. So these shots, the individual units, can basically be just recordings or video portions of your video stream between camera cuts. This may be one way to look at it. Or these boundaries or borders between shots can also be defined in more content-based ways, like capturing motion, the existence of objects when a new object enters into the shot, etc. So the segmentation in this case refers to temporal dimension, segmenting in the time domain, in other words, grouping, categorizing frames, successive frames, into shots or units, which can be based on simple, crude pixel differences, pixel amplitudes of signals. In other words, histogram comparisons when there's a major change in the color distribution. You can localize these histogram comparisons and look at certain areas. Look at motion vectors when there's a lot of motions or a new motion introduced. Some of these features, by the way, pixel differences, frequency domain metrics, histograms, and motion vectors, also like these CT coefficients, are also used for coding purposes or low compression. So the features are already available for you, even just for basic representation purposes, coding purposes. So those features can readily be used for AI applications or indexing or retrieval mechanisms, as well as just pure representation of video. For example, MPEG compression, which is the motion or video version of the popular JPEG, will take into account the motion or the change between successive frames. In other words, if an object is moving, you don't encode every single image independently, because successive frames are so much correlated with each other. You don't actually have to reinvent the wheel, so to speak, right? So every frame is very similar to the previous frame, so you only encode the differences between successive frames. And this can give you a much higher efficiency in encoding. So video representation can be a lot more efficient, taking into account this high correlation between successive frames. And for doing that, you need things like motion vectors and histograms and DCT coefficients. DCT is the discrete time transformation, cosine transformation. So these are frequency domain coefficients you need to represent the image in an efficient way. The same basic data can also be used for video retrieval mechanisms. That's the main point in that previous slide. So once you segment your videos into shots by taking into account either the distance or dissimilarity between frames. If this goes above a certain threshold, then you can tell that a new shot is starting. So these are also called camera cuts sometimes, if these are recordings in a movie, for example. So once you have that shot representation, the representation of indexing and retrieval mechanisms can be based on different features. So the frames, so staying purely in the image domain, you can look at these key frames or representative frames and assume that they best represent what is contained in that video shot, in that portion of the video, and you can rely on those image features. Or you can look at the motion information to define the events in this case, and look at not necessarily just the visual features, but also the dynamic features, the movements, etc. The objects, just like images, can be also an important part. So different dimensions, different aspects, a lot of times a combination of these features are used in the literature to index and retrieve videos from a database. So one of the easiest and cheapest in terms of computation is to rely on the representative frames. So looking at, since there are many image-based indexing and retrieval mechanisms, you can just basically borrow from those ideas, and assuming that you have a good, reliable method to choose your representative frames, then your video indexing and retrieval mechanism can be based on those images alone. But as you can imagine, this gives you only a limited description of what may be contained in those videos. A lot of times, just a single image represents only a small portion of the semantics that may be involved in that video shot or video sequence. And there will be some key questions like how to choose these representative frames, and if you have multiple frames, how to handle them, in multidimensional, retrieval mechanisms. So the methods based on these representative frames will heavily rely on, a successful selection mechanism for these representative frames. So there are different methods to choose, like from a shot to either choose the first frame, and looking at the color representation. So the most maybe distinctive frame from a sequence of frames that you may deem that best represents, especially the visual aspects. You can look at the color distributions and come up with the most so-called prominent image representations, or simply take the average of the histogram. So different methods have been tried, the comparisons on how successfully they can represent. So depending on the obviously content, one method or the other may be superior to each other. Again, we won't get into all the technical details, but representing videos by keyframes or representative frames is one of the approaches here. Or looking at to treat the different areas of these images, representative images, differently for foreground and background. So a lot of times an image, a single shot, will have a lot of details in the background that do not really add much to the description. So the foreground materials like moving objects or maybe people may actually be much be more relevant and more important in defining the content. So the foreground and background separation and taking them into account is another improvement or enhancement to this. So you can use different techniques to differentiate the foreground from the background. So you see that in your Zoom calls too, right? So you can blur the background, and they use, those video conferencing tools use some simpler version of these methods to tell what is really important and should be kept alone, and the background that should actually be blurred, so that you don't necessarily pay attention to that. And also you can save the data by simply not transmitting a lot of the full background material.
Yeah, and they can change what's interesting is they can change the background. Students, you have the student in the foreground and they've chosen a beach background. Yes.
So once you can tell what is foreground and what is background, you can either blur it, remove it, or replace it with other material. So this can provide advantages in encoding the video. So you only encode the foreground material and not worry about what is in the background, or in representing what's important for indexing and retrieval mechanisms. You can basically just focus on the foreground material, which will make things both more effective and more efficient. And again, we will not worry about the specifics of the methods here. So the other dimension, non-visual dimension, typical in video, which was my focus of my research a while ago, was to take into account the motion or the dynamics. Right? So this is one of the key distinctions between a video stream and a single image. So a single image, you can maybe interpret different motions, but does not necessarily naturally contain the components of motion. Nothing changes in an image by nature, right? But a sequence of images, a video, typically does involve, if there's no motion, if all images are the same, then that's not even a video, right?
Yeah,
So typically what defines a video stream, or what differentiates a video, is actually the dynamism or changes or the motion, whether that's the entire background or the frame being in motion, or individual objects moving with respect to each other. So to best capture the contents or the semantics in a video, you also need to take into account the motion dimension. So this motion can be in the form of just camera moving, so the entire frame may be moving, but also in terms of panning, tilting, zooming in and out, etc. But also the individual objects may be moving, which will define in many cases the contents or the meanings of the recordings that will be contained in that video. So you can look at the motion from a more global perspective, how much motion really is involved and things like this. Or simply looking into it, the number of or the ratio of pixels that seem to be in motion. Or you can look at the individual objects and their movements and try to develop some understanding. So the uniformity of the smoothness of the motion can be one dimension here. So the global motion, left to right to left, this is called panning. Of course, this is in most cases resulted by camera movements, unless the whole scene is being moved. And tilting is another dimension. So you can very easily capture these global movement or motion information aspects. But things can get more tricky when you have to deal with moving objects, which will be very much the case in defining also the contents or the meanings of the content-based description of the video content. So if you have objects moving in your video, which will very often be the case, you will need to have some kind of a indexing or representation mechanism of those not just the object information, but also the emotion, the nature of the emotion, maybe relative movements, etc., and how that can lead to the higher level description of the video content and allow retrieval mechanism. So in sports videos, for example, if you're looking for a certain move, all the slam dunks in a basketball game, some description like based on on the movements or even relative movements of objects can best and only be defined and carried out by taking into account the objects and their relative movements. So both the physical location within the image space, two-dimensional space, and their relative movements, interactions. So for us, it's maybe easy to capture and identify slam dunks, but if you're trying to have an algorithm capture all these from a collection of thousands or millions of video recordings, these techniques can be a bit more tricky. So if your retrieval mechanism is based on objects, which will also involve their relative positions, movements, etc., you don't want to just rely on the still object segmentation, identifying from a single object, a single image, but from a video sequence. So identifying their movements and capturing that and integrating that into your indexing and retrieval mechanisms will be critical, which can utilize some of these encoding mechanisms like MPEG-4 has object-based coding standard, which can provide you with some basic information, and then from that you can build video indexing and retrieval mechanisms, which is very typically done in the literature. You'll find a lot of projects doing just that. But most video database systems, in addition to the imagery features that or the visual features that image databases or image data management systems will take into account, we'll also need to have the interframe analysis, basically the motion analysis, as well as the object tracking information into account. So the spatial abstraction here refers to mostly image or visual features and will be typical for image databases also. And we talked about some of these components in more detail before. But what is a little different in a video database system is the addition of the temporal dimension and the implications that come with that, including the motion analysis and the higher level descriptions like the events that are the result of these intra-frame or motion or dynamic aspects that you will find in videos or a sequence of frames. So the video database system or video management system or video data science applications will need to take into account both the spatial and temporal aspects, often referred to as spatial temporal semantics, that will basically come up with that description of the content for further content-based retrieval mechanisms. So if you're trying to capture, for example, detect the slam dunks from basketball videos, so you cannot just rely on just a single image shot and and conclude that this is a slam dunk video, right? Unless that happens to be just at the right moment. But using both the imagery features, looking for a ball, obviously, and the player holding that ball at a certain height, and that being at a certain sequence, they're jumping first and then just put the ball through the hoop, etc. So you can define that event as a sequence of certain descriptions along the temporal dimension, in addition to some object definitions or scene descriptions based on still images. So you will typically have a combination of these spatial or image features and the temporal or dynamic aspects in video data system. So that's typically what differentiates a video database. So this is just one example that was the subject of my research when I was a graduate student. So, and that once you have that kind of a description, the next step, of course, is to allow in a retrieval mechanism, a video database, basically querying and retrieval mechanism to allow the users to represent what they're looking for. Things like slam dunk or other descriptions. So you want to allow some kind of an interface so the users can define what they're looking for, not necessarily just by example videos, which can be done easier, but also to allow them with ways to visually describe what they're looking for. So this, depending on your database collection, what is in your video collection, the ways to describe those may differ. So if it's football clips, you may be looking for interesting events in football games. If it's basically just airplanes flying, you may be looking for certain formations, which can best be described by maybe some kind of a sketching user interface. So again, we won't get into all the details, but this is an interesting comparison between the levels of abstraction and the level of granularity between different techniques used in modeling of the semantics in multimedia data, from image recognition to video parsing, knowledge-based event modeling. This is the highest level of abstraction. Obviously, you would be looking for things like specific events or security situations, etc. But the granularity in terms of the physical representation of data is the highest with the image recognition. So you're relying most physical data you obtain in the case of image recognition. But for higher level applications, that level of abstraction can be higher. So the video content can also be modeled based on its motion and movements and the semantics that are implied. So that we call that spatial temporal logic that takes into account both the, again, spatial and time-based temporal aspects. There is a querying mechanism that developed as part of this. Just to give you an example on how you can represent motion with different models, trajectory using the trajectories of the objects as they move. For example, the slam dunk. In the case of slam dunk, if you basically just isolate the movement of the basketball, that may define that particular event. It's the trajectory the ball follows may be part of that description and may help you detect those videos that contain what you're looking for. Since there is both a spatial and temporal domain, some directed graph models like what we call VSDG can play an important role. This is again a higher level description of the scene. So rather than relying on pixels, etc., you're just extracting the important aspects of your video, just like foreground, background detection. The interesting objects, this may be a ball, this may be a player that may appear in the same segment, and the horizontal direction here is the time. So two objects appearing in the same segment almost at the same time in your video stream, and then in the next scene, there may be some other objects appearing. So just this kind of a simpler, higher level representation of your video may actually allow you to base some of your indexing and retrieval mechanisms, like capturing videos with a slam dunk or some other interesting event. Another model that we had looked at was the trail left behind by objects over a sequence of frames. So these trails a lot of times actually and their shape, etc. Maybe another reduced dimensionality representation of your video sequence. Much simpler than, of course, a whole bunch of frames in terms of data and also, but then this again just gives you a simpler representation that may actually give you the clues about what you're looking for. And this is called a trail model, and then this can, of course, allow you to successfully represent certain events or aspects of your video data. So this was basically a touchdown event that can be represented by objects and their both spatial and temporal domain interrelationships. And this is just the architecture of that system called the system that we call picturesque. This was actually an acronym: Pictorial Information and Content Transformation for Spatio-Temporal Queries, something like that. So the different models have their advantages and disadvantages. One interesting note here is that these frequency domain transformation techniques like Fourier transform are not always scale invariant. There is this transform technique called Mellin transform that is scale invariant, meaning objects with different sizes in spatial domain can actually be represented with the same features in Mellin transform. So if you're looking for a wall or a triangular object, for example, whether it's a small size in your image collection or video collection or large size, a triangle will have, whether it's large or small, will have the same representation in the Mellin transform domain. So that can provide you with an interesting scale invariant representation of your objects in both spatial and temporal dimensions. And also these relations along a certain dimension, whether it's spatial or temporal, can also be important again as another high-level description. So these 7 different possibilities between 2 intervals, one coming before, meets, overlaps, during, starts, etc., all these combinations, can also be an interesting high-level description. For example, if you're looking for events, a slam dunk happening before a touchdown or some other, or during or just right after, these descriptors can also be play an important role in high-level descriptions or representation of schemes. In the spatial domain, they can allow you to represent relative positioning of objects. So if in your acrobatics, if you're looking for certain formations, that formation, that specific formation can be represented by a collection of these relationships, inter-object relationships happening among your objects. So from your millions of pixels and raw descriptions, you can go to these intermediate descriptions like these relations in the space or time domain, object movements, trail representation, etc., or graphical representations such as these. These are just some of these examples, what we call the BSDG, the representation in the time domain. So if you go from your raw dimension, the raw representation of just pixel values to these intermediate representations, you can actually make it possible to treat your video or multimedia data, whether it's just images, collection of images, audio tracks, or of course video. You can basically treat your multimedia content as a database. And those intermediate representations can then make it possible, depending on how successfully they capture the semantics and what you need to capture or index in your data, they can make it possible to build your data science or data retrieval or database applications, to build and to treat your raw content, media, multimedia content, just like any other alphanumeric data that you can base your traditional data applications on. So that was the main point. I tried to go through some examples just so you can visualize, so as to say, some of these ideas and concepts to utilize multimedia content within the data science and database applications area. So our plan is to also have a discussion later in the semester on IoT-based data, which is not exactly multimedia data in a traditional sense, but that will be another dimension of non-traditional data being included in some of the data science applications. So we're done with the multimedia part. If there are any questions or any comments, I know I didn't leave much time again, but we will welcome any questions or comments. We have 3 projects in our Blackboard content area. They deal with, 2 of them are on images. One has to do with video collections for shot detection. So you're welcome to choose one of those 3 projects, and let me know if you have any questions regarding those. You can always feel free to reach out to me or to Dr. Pierce. And hopefully you'll find those projects interesting. And any questions or any clarifications you need about them, please do let me know.
Well, very good. And I'll just add on that next week, I'm going to do some demonstrations, just some simple image data science tutorials. And we'll also talk a little bit more about the techniques in that image assignment. So let me put it this way, I think after next week, once you see some of the Kaggle tutorials we'll take a look at in class, and once we talk a little bit more about some of the readings next week, which talk a little bit more about some of these different techniques, you'll probably find the image assignment a lot more doable. And one thing that you may find is, I'm thinking for the images, you probably want to have an image versus a graphic. I am thinking that you'll find that particularly when you're trying to do things like thresholding and things like that, I think it's easier, it's maybe easier to see the differences with an actual picture versus like a vector graphic or something.
And yeah, if you're doing it, for example, in edge detection, it may be better to take your own pictures, maybe put a few objects like books, phone, etc., with defined edges around the boundaries, and apply that that method on an image that you're taking. That may be a better representation of what you're trying to do.
Right. So if you're looking for, so I think some of these examples work better if you actually have an actual picture versus a cartoon or something like that. So, yeah. You never know what you get, though.
Yeah.
But we'll take a look at that, and we'll also, I was going to say, one of the things you'll notice is in this area, if you're going to work with pictures, you can see how much processing there needs to be done before you can use some of these techniques. And it'll be very interesting to see as the libraries and functionalities get better, just like the large language models are getting better at taking the customer chat and just doing the extraction for you. It'll be really interesting as we get into the AI area. Will they have basically, I want to say, large language models for video and it's like that will make a lot of these capabilities a lot better. Yeah.
There's a question about how practical this is in making part of the search applications. Many, I just showed one example. Of course, that's the image example-based search Google site has. Many of these techniques are still part of experimental systems. So when you go to these special sites and so forth, you can actually have some video or image-based searching and try it out. But the mainstream search engines are still kind of looking for ways to make it more practical. Beyond that goes beyond keyword-based tagging of videos and images. So we have come a long way in relating certain keywords to images and videos, and that's the basis of most searching. The mainstream searching applications. But I think as videos and images are becoming more mainstream, parts of the data collection, which they already are, we will also see the retrieval and searching mechanisms integrated to things like Google and others. So we may see a video example-based searching or other searching mechanisms, just like the image-based searching example we discussed last time.
All right. Very good. Well, we'll see you all. Have a great weekend. A little nicer weather. Even next week, it'll be a little cooler, but still, I think we're past the snow.